Hello everyone, welcome to Kepler. Today we will be reviewing the problems for the contest Educational Round 184. So let us jump into the problems. The first problem, it is given that Alice and Bob have a bag with n marbles with integer vi written on the ith marble, and also Alice and Bob each have an integer a and b. Now they play the game. Basically, they draw any ball from the bag, and the point goes to the one whose integer is closest to the marble. So it is the value of a is already given, so Alice has already picked her integer, and we must find out which integer Bob should pick so that his score is maximized. So let us consider the example we have. It is given that a is 21 and our array is 10, 20, 20, 30, 40, 50, 60, 70. Suppose Bob picks 11. In this case, there is only one element in the array closest to Bob, which is 10. For all the other elements, for example, for 20, between 20 and 21, there is a distance of 1. Between 20 and 11, there is a distance of 9. So, the point 20, the point will go to Alice. And similarly, for all the numbers from 30, 40, 50 to 70, the point will go to Alice. So, we need to pick a B such that Bob's score is maximized. So, if you have picked, say, B equal to 31, say, in this case, this entire set we have here will be closer to Bob than Alice. So, Bob's score will be 5. And for Alice, 10 and 20 will be closer to Alice. So, Alice's score will be 2. This is the optimal case. So, let us look at a few cases we can have. If say a of I is say let's or b of I. Let's say value of the marble is equal to Alice's score a. In this case, Alice will always get the point because the distance between vi and Alice is 0, and regardless of what Bob makes, he cannot get this marble, because in case of a tie, Alice always gets the point. Now, if vi is less than a, say, in this case, B will get the point only if Bob will get the point only if B is greater than A. Otherwise, if vi is less than A, Bob can get the marble if B is less than A. So, if we just look at this case, for example, in this case, Bob managed to get all the elements after A, so these 5 elements, because his 31, his score value 31 was greater than 21. In case of 11, he got a number less than A. So, basically, if Bob picks A plus 1, he will get the entire set of elements greater than A. If he picks less than 1, so A minus 1, he will get all the elements less than A. So, we can just compute the count of these two values, and based on this, we can pick one of these two integers as the answer. So, let us look at the solution really quick. Yeah, so we have two variables where we store the number of marbles greater than A and less than A. If number of marbles greater than A is more, we will choose Alice plus 1, otherwise Alice minus 1. So, pretty simple solution. Now, let us look at problem B. For problem B, it is given that you have a string S, and the string has it represents a stream, river stream. So, for example, if it is this less than sign, then there is a leftward current. Otherwise, in case of a rightward sign, there is a rightward current. Otherwise, if there is an asterisk, it means there is no current. So if there is a current in the cell the player is at, he must move to the neighboring cell in that direction. Otherwise, if there is no current and asterisk, he can choose between the right or left cell. He can choose which cell he wants to move to. So we have to find the maximum amount of time it will take for the player to go out of bounds of the string, or he can, if he can infinitely stay in the string, print -1. So let us consider a few cases for this. For the first sample test case, we have an array of enter asterisk. So in this case, the player can start anywhere, and he can just keep looping around the 2 asterisk position. For example, if he starts at the middle position here, he will first go right to this position, and then he will go left, again right, left, and so forth. So he can sort of keep looping here, and it will be infinity. So the time will be infinity. He can stay in this stream infinitely. Suppose in the second test case, for example, he had this. In this case, the player will always move out of bounds regardless of what he picks. So if he picks, for example, this index, he has to go to the left index here, again left, and finally out of bounds. So in this case, time is 3. So first, let's analyze when exactly we'll have an infinite traveling time. If s of I is equal to if we have this pattern in the string, 2 asterisks side by side, in this case it is infinite because we have showed that if there are 2 asterisks, we can just keep looping around these 2 positions. Similarly, if we have this, then also we can stay infinitely because it is the same logic. We can just keep looping here. It's just that in this case, the player will be forced to go to the left cell, and then the player can just simply move back to right cell. Similarly, in this case also it is infinite, and in this case also left right side by side it is infinite. But this one is not valid because in this case the player will get shifted out of after these 2 cells. So this one is invalid. So we have these 4 patterns. If any of these patterns occur in the string, then we have an infinite traveling time. Now suppose you have checked a string and this pattern does not occur. So now what is the time? It is a traveling time for the string. So if it does not occur anything like this means our array is something like this, a bunch of lefts in the beginning, maybe an asterisk here, and then a bunch of rights like this. Right. So basically, intuitively what this means is, regardless of where the player starts, he will be pushed out of the boundary depending on if he chooses left or right. So what we can do here is we will find the number of lefts in the beginning we have, and the number of rights in the beginning, and the answer will basically be the maximum of the left part or the right part. So for example, in this case, for example, we had more lefts we have 3 lefts on this side and 2 rights on this side. So our answer for this was 3. Surely if our answer is something like say this, in this case answer is 4 because we have 3 rights on this side and we're adding on extra for this asterisk. So this can be solved using a simple 2-pointer approach. We start at the with L equal to 0 and R equal to -1. We increment L until we find the rightward pointer. Similarly, we decrement R until we find the leftward pointer. And based on this L and R, we can find out exactly on which side there are more currents. So let us look at the solution really quick. Yeah. So this is the first check I was talking about. So we are just checking if the port patterns I mentioned occur in the array, in the string. If it occurs, we output -1 in return. If there is no infinite pattern, we will check from each side how many rightward, how many leftward streams we have on the left side and rightward streams we have on the right side, and we can take the maximum of these two to get the final maximum traveling time. So now let's look at the next problem C. For problem C, it is given that we have two integer array of length n, and you have to choose arrange L and R and update the array according to this rule. For each element in L and R, we change it to L plus R. So we have to perform at most one operation and maximize the sum for the entire array. So if you look at the sample test case we have at the end, we have this example 0, 3, 2, 0, 9, 10. In this case, the optimal operation is 2, 3. So initially, the sum for this was 3 plus 2 plus 0 plus 9 plus 10 equals 24. If we perform the operation 2, 3, it becomes 3, 2, 3, 5, 5, 9, 10. This is the sum is 3, 13, 22, 32. So have to find out what is the maximum, what is the optimal operation so that our final summation is maximized. Suppose we perform an operation on the array L to R. For the array L to R, the original sum was summation of L to R AFI. We can rewrite this as a prefix of R, minus prefix of L minus 1. Here prefix is simply the prefix summation of the A elements. So sum of the first R elements minus sum of the first L minus 1 elements. The new sum will be R minus L plus 1 into L plus R. So this is just a number of elements, R minus L plus 1 into the new element. We can expand this to get the following equation: R square plus RL minus L square minus LR plus L plus R. We can cancel out these RL terms. So we can sort of get this R square plus R plus minus L square plus L. So this is the new sum which we get after performing the operation. So now let's calculate the difference between these two. So difference equal to the new sum minus the old sum. So R square plus R plus minus L square plus minus prefix of R minus prefix of L minus 1. Now we'll sort of rearrange these terms, make it like this: R square plus R plus prefix of R plus minus L square plus L plus prefix of L. So we have sort of separated the R terms and the left terms into a separate section. Let's call this value Pi. So let's say P2 of I, and let's call this one P1 of I. So P2 of I is simply I square plus I plus prefix of I, and P1 of I is minus I square plus I plus prefix of L minus I minus 1. So we can compute this P2 and P1 values independently. Now suppose we are trying to find out what is the best operation when we fix the R index. Suppose for some R, this difference maximum will be P2 of R minus some P2 of P1 of L. Now this P2 of R is fixed, so we must find the best P1 of L, P plus P1 of L, the best P1 of L given L is less than equal to R. So basically we must find the maximum of P1 of L given this. So this can be, so if you can if you are following the entire solution, you will see that this can be easily computed because we have already computed P2 and P1. So for each R, you will take P2 of R and the prefix maximum of P1 up to R. This will give us the best possible L position. Right. So for each R, you will compute the best possible difference we can get using this operation, and we can take the maximum value among all these R values. So let us look at the code to get some better clarity. So as I discussed, I am first iterating through the array. In P1 of I, I am computing prefix minus I into I plus I, and for P2 of I, I am computing I into I plus I minus prefix. Yeah, this should have been minus 1, but yeah, it's the same. Prefix. So basically, I have another variable mx here. So now I iterate from 1 to n, and as I iterate, I store the maximum value of P1 I've observed so far, and I update the answer as maximum of answer, and P2 of I, the current R index, plus mx, the maximum P1 value I've observed so far. So this gives us the maximum difference we can get after performing the operation. So we add the entire array sum to this, and we get the final answer. Now let us look at problem D. So for problem D, it is given that we have a sequence of integers from 1 to 112. And we want to, basically we're performing x operations on this. For each operation, we simultaneously move all numbers at positions y, 2 into y, 3 into y, up to m into y. And after performing all these operations, we want to find the kth number remaining in the sequence, or the kth number in the final sequence. So let us consider the example given here. X equal to 2, y equal to 3, and k equal to 5. Suppose the array is something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now in the first operation, we will be removing every third element. So 3 gets moved, 6 gets moved, and 9 gets moved. So the elements at every third position. So the array becomes 1, 2, 4, 5, 7, 8, 10. Again we do the operation. So the element at third element gets moved, and the sixth position gets moved. So 1, 2, 5, 8, 10. So this is the final elements you are left with, and the fifth position there is the element 5. So in order to solve this, let us think about the reverse operation. So suppose instead of removing every white element, we will insert a new element in the white position. So for example, if we had this final array, we can perform the reverse operation to get back the previous array. So at the third position, we insert an element 4, 5, 8, and again we insert an element. Sorry. Additional is safe. Yeah. 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 So this is 7. Yeah. So it is 7 here. So 5, 7, and after the sixth position, we insert the next element. So 8, 10. So basically, you have reversed the first operation. Again, if we again apply the inverse operation on this, we get the original sequence of 1 to 10. So suppose we have a sequence of length z, say. If we apply the inverse operation, by how many elements does this length of the sequence increase? Since we are adding an element every y index, so this will become z plus z by y. Right? Z by y. Suppose we call this function z. So f of z equal to z plus z by y. Now, here we need to find the kth element, right? So suppose we start with the let's say we want to find k equal to 5 in the original case, and suppose for now, suppose we have just one operation x equal to 1, y equal to 3, right? We know that suppose we f of k minus 1 is equal to f of 4. So suppose in the final array we have these 5 elements, a1, a2, a3, a4, a5. What we can do is we can apply our function on the number 4, the length 4. This will give us the length of this segment before removing all the elements. So for example, in this case, for 1, 2, 3, 4, if we apply on 1, 2, 4, 5, we get the previous version. So f of 4 is 4 by 3, 1, so 5. So there was one element more for this. So I will make a claim here. My claim is that the kth element in the final array is basically the f of k minus 1 plus 1th element in the original array. To understand why this is happening, notice that when we apply the operation, basically the length of an array goes to this, the length of a segment goes to the original length it had. So if the array has k minus 1 elements in the final case, it will have f of k minus 1 elements in the initial sequence before removing. So the element immediately after this will be the element we're looking for. So to maybe make things clear, let us consider this example itself. Suppose consider for x equal to 1. Suppose we are looking for the fifth element. 1, 2, 3. Suppose we're looking at sixth element. Okay. So after we compute f of 5. So suppose we're looking for a seventh element, right? Equal to 7. So f of k minus 1 is f of 6, which is 6 by 3 plus 6. Okay, so there should be a correction here. This should actually be 1 y minus 1, because if you notice what we're doing here is, after every y minus 1 elements, we're inserting an element, new element to the sequence. So f of z should be f of z should be z plus yeah. So f of z should be z plus z minus 1, sorry, z by y minus 1. Y minus 1 because since we are inserting at the ith position, the yth position, basically after every y minus 1th block, we are inserting a new element. So for in this case, f of 6 becomes 6 plus 6 by 2 equal to 9. So our target element should be at the 10th position in the original array. So the answer is 10, and we see that even in this, after performing the operation 1, 2, 4, 5, 7, 8, 10, this is in fact the correct answer. This is the 7th element. Similarly, suppose from the original question, for example, we want to calculate it for k equal to 5, sorry, and x equal to 2. So we will again reapply this operation on this. We'll apply it 2 times. So we'll first compute f of 4, which is 4 plus 4 by 2 equal to 6, and then f of 6 is equal to 6 plus 6 by 2 is 9. So the 9 plus 1 equal to 10th element is the answer. So basically, our answer is f of x to the power x of k minus 1. So this means that we apply this function uh, f of k equal to k plus k minus 1 k by y minus 1 x times to get the final answer. So for the first d1 case which we had, for d1 I think the constants were up to 1e5. So in this case the complexity comes out to order of x, and this is fine because x is up to 1e5. So we can comfortably pass all the test cases. Now for d2 it is x is equal to 1e12. So now we need to optimize it somehow to make it faster than order of x. So to understand how we can optimize it, let us first look at another test case. So let us look at the original test case we had and modify it a bit. So suppose x equal to say 5 and let's say something bigger, say 5 y equal to, let's say y equal to, let's say 12 and k equal to, let's say 30, let's say, or yeah, 30. Okay, fine. Okay, so as we're doing, we will first compute f of k minus 1, which is 29 plus 29 by 12, which is 29 plus 2. Then again f of 30, yeah, f of 31, which is 31 plus 31 by 12, which is 31 plus 2. Then f of 33 plus 33 by 12, which is 33 plus 3. F of 34, sorry, 36 is, sorry, this is also f of 33 plus 2, sorry. Again f of 35 is 35 plus 2 again, and finally f of I think 1 2 3 4, we need 2 more operations, so f of 37 is 37 plus 3, and f of 40 is 40 plus 3. I think we perform one extra operation, but it's fine. So basically we are in the same process we discussed, but what I meant to show here is that you will notice a lot of the times the increment we are doing on the length is the same. For example, here we incremented it by almost by 2 almost 4 times. Again, for 3 it will be incremented by 3 times, and we should go on like this if we keep on this, keep the series going further. So what this means is, while the value of x is very large, there will be a lot of repetitions in the increments you are doing. So let's see how we can optimize this further. So given that we were starting off with k minus 1 equal 29, we know that for this k of phi is 2. Let us compute how many times you have to add 2 to increase this k by y value. So this will be k minus or k plus q minus 1 by q times, or simply this is basically the k by q ceiling basically. So we have to find out how many times exactly we must increment. You have to increment by 2 so that k by y becomes 3. For example, here we have to increment it by 2 4 times before it became 3. So what we can try to do is, we can try to group up all this instead of going one by one. Find out how many times we will increment it by 2 immediately and perform these operations together. Right. We can perform all these operations together. So for this shift, we can just bring it here. It was 29, 31, 33, 35, 37, 40. Yeah. Okay. So what we can do is, suppose we declare a threshold. This threshold is 36. So what this means is, as long as my length is less than 36, my increment value k by y will be equal to 2. So instead of manually incrementing it by 2 for every x for all the iterations of x, you can calculate what the threshold is, which is so suppose the current value of the increment is k by y. We compute the threshold equal to q plus 1 in times y. So our number of increments with this q value is the threshold. Let's call this q2 for example. So number of operations is q2 minus q by y. For example, in this case 36 minus 29 by not y, sorry, by q, my bad. So q2 minus, so q2 minus current integer by y. So for example here 36 minus the current integer 29 by this should be not y, it should be the q value, so 2. So in this case our q is 29 by 2 equal to 2 and the threshold is 3 into 12 equal to 36. So this comes out to 7 by 2 equal to 3. Or we'll be taking a ceiling, so it's 4. So if you notice, this is basically the number of times we actually incremented by 4 in this case. So instead of directly iterating x times, we compute the current increment q, see that in order to change it to q plus 1, how many times you have to increment it using this formula. So let's look at the code to get a better understanding. So we first start with n equal to k minus 1 and c equal to y minus 1. Now the while we basically iterate a loop while x is greater than 0 and m is less than equal to 1 to 12. We calculate the current increment m by c, which is just k minus 1 by minus 1. Then we compute the next threshold q plus 1 into c. We compute the difference and we compute j equal to basically the number of j is the number of times you have to increment with q so that it crosses this threshold m next. If and so based on this we can directly increment in x q this j times and direct x by j. Now you might be wondering why exactly this is more optimal compared to our initial approach. Notice that for every if the ith iteration we increment it by qi, in the next ith iteration we'll increment it by some other integer qi plus 1, which is always greater. Now if we think about the sum of the first n plus n integers 1 2 3 4 5 6, suppose these are different q values. So what is the formula for this? N plus 1 by 2, right? So basically this is the worst case. Ideally our q values will be more spaced out than this, but suppose in the worst case it is something like this 1 2 3 4 5 6. So what this means is our n plus 1 by 2 value we are incrementing so we can increment it up to 1 to 12, right? So n is around less than equal to 1 will be around 1 is 6. So the actual number of loops, the iterations for this entire process will be actually order of 1 is 6 because of this property. The actual bound will likely be much better than order of root n, but this basically proves that this process works much faster compared to initial approach of directly routing to x. So that was all for the today's contest. I hope you enjoyed the explanations for the problems. If you like the explanations, please do comment and like on this video. Also, you can please check out the website for Kepler. You can find the link in the description box below. You can find the notes for this video as well as other resources from the Kepler website. And that's all for today. See you in the next video. Thank you.